interpolation to get a signal that we want to send a series of bits from a transmitter to a receiver. So in this part one, we talked about introduction of mapping from symbols of bits to symbol amplitudes, and then from symbol amplitudes to pulses for transmission. We talked about different pulse shapes briefly, and there is something special about the type of impulse response we want out of the interpolation, the pulse shaping filter, also known as the interpolation filter. Today we'll talk more about pulse shaping, do pulse shaping filter bank, and then some design trade-offs. Okay, so this was, let's just go right to where we left off. We left off at 13-8, and the application here is digital audio, but it's the same idea. It's going to be discrete time interpolation. We have samples that we know at a certain rate, and we want to generate a similar discrete time signal, but at a higher rate, and we want to maintain the information that we had originally at the lower sampling rate when we go to the higher sampling rate. When we go to the higher sampling rate, we also want to reduce the artifacts that we introduce when we jump from this lower rate to a higher rate. And this is a general idea, not just in signals that have a notion of time. This works in image processing. If I want to increase the image size by a factor of 2 along the rows and a factor of 2 along the columns, we can apply the same approach here. Okay. Now in image processing, if we apply the same approach, we get a blurred image. There are other ways and better ways to do it, but the same approach can be done. Okay. So let's go through this example from the beginning. We got through some of it last time. So again, this is a general issue of discrete time interpolation, and one of the reasons we want to do this entirely in discrete time is the alternative is to take our discrete time signal that we start with, in our case, an audio CD signal, could be an uncompressed MP3 file. MP3 is actually MPEG-1 layer 3 audio, in case you're wondering. So MP3 is, which is from 92 actually. It's a pretty useful but older standard. So we uncompress the MP3. A lot of those MP3s started life as an audio CD track at the standard 16 bits per sample and a sampling rate of 44.1 kilohertz. And in this demonstration, I just show you one channel of the audio, not two, not both. Okay, so we want to take, in this particular case, and we'll see why this is important when we do data conversion in lecture 10. But this is a way that we can go to a higher sampling rate, which gives us oversampling for free. Well, not for free, almost for free. A little bit of complexity to do it, but we get a little bit of oversampling as a result. And using that oversampling, we know oversampling is a good thing for lots of reasons. One of those reasons is we're going to actually, in data conversion, inject noise, surprisingly, to improve the signal quality. And this gives us some place to put things like quantization error, noise we inject, into frequencies we can't hear. Right? So we can hear, normal hearing, 20 hertz to 20 kilohertz. And this is normal hearing on average over lots of people tested. So there are some people that can hear outside this range. Anyway, so normal hearing, 20 hertz to 20 kilohertz. So if we use oversampling, then the advantage here is that we're now working with a lot of frequencies that we can't hear. So we can put all kinds of stuff in those frequencies we can't hear. We can dump noise, quantization artifacts, harmonics, and we'll do that later on in data conversion. And we'll filter them out in the end, but there are frequencies we're not going to hear anyway. All right, so let's go through this process. So in this particular example, I want to increase the sampling rate by a factor of 4. So I want to go from a standard audio CD rate from the 1982 standards for audio CD to a higher sampling rate. So in this case, it's 4x increase. And I want to do it in a way that manages the artifacts that I introduced in doing this rate change. So from a linear systems point of view, the first thing I'll do is upsample by 4, and then, which is going to introduce artifacts, and then I'm going to filter out a lot of those artifacts. Standard low-pass FIR filter, and we'll talk about the cutoff frequency a little bit later, or the stop band frequency at the bottom of the slide. But it's going to be it can be a fairly conventional FIR filter design, low-pass, Parks-McClellan, Okay? Or we could go after a different pulse shape. Right? We could use a specific pulse shape if we wanted to. So let's go through the pictures on the right to see kind of what happens. So first, I start with my lower rate input signal, and I want to send that through an upsample by 4. This upsample by 4 will increase because I'm going to introduce 4 times as many. I'm going to have 4 times as many samples on the output of the upsampler than at the input. So I'm going to have 4 times the sampling rate on the output of the upsample by 4. So what's going to happen? So the input to the upsampler I show in this discrete time index little n, and we use a different index after upsampling. We use n prime. So here are my samples to the upsample by 4 in the first discrete time index little n. So my first sample arrives. It's copied by the upsampler to its output unchanged. So there's no error in that. It's just a copy at the same number of bits per sample as the input signal is at. Then I'm going to append L minus 1 zeros, where L is the upsampling ratio, or upsampling factor. So I'm going to insert, in this case, L minus 1. That is to say, I'm going to insert or append 3 zeros. Next sample comes along at index 1 in the space of little n. It gets copied as is from input to output by the upsampler. So the upsampler doesn't have any multiply, accumulate operations. It's just a copy from input to output. And then I'm going to append the 3 zeros. And I'm going to do this over and over again. It's very periodic, or it is periodic. And then finally, well, in this example, it would, in principle, continue indefinitely. Right? So now the next sample comes in, it gets copied, and then, of course, I don't show the 3 zeros that get appended, but they are there. And we just do this over and over again. And so the result of the output of the upsampler is 4 times as many samples as we had on the input. So that you can see visually. Now, what's the downside? What's the problem with the output of the upsampler?
3 artifacts per sample.
I got 3 artifacts per sample? 3?
3 artifacts per sample.
I have 3 artifacts. I could, okay, can you tell me what those artifacts are? Zeros? And why is it an artifact?
It's not the original signal.
Yeah, it was on the original signal. So so the good news is we're increasing the sampling rate by a factor of 4. The bad news is we've just inserted a bunch of zeros because we have no idea what was there, right? Per se. I mean, we will have some idea in the next step. But the upsampler has no idea what was there. Just blindly insert zeros. Okay? Now, so what are the artifacts? Well, if you look at what happens from the sample we know at index 0 to the sample that we've inserted at 0, there's a sudden jump, right? Yeah, that's fine. Okay, so the sudden jump here goes from some value down to 0, and then it takes a hard turn. All right, so those are going to be high frequency components. It's going to be introduced here, and that's going to sound, well, we're at an audible range. We probably won't hear all the audible effects on that one, but we'll certainly hear some harmonics. If this is a periodic waveform going into the upsampler, we'll hear some harmonics of that, most likely. But it's a distortion, and so we get back now. We can remove a lot of these artifacts. Certainly, any ones that are at frequencies beyond a value we didn't have to begin with, simply by filtering, and nothing more. Okay, so if we look at what we had before, our initial sampling rate, which is 44.1 kilohertz, means that our maximum frequency possible has to be less than half the sampling rate. And this is the sampling rate of 44.1 kilohertz. So the maximum frequency present in this original signal that we're starting with is frequencies less than 22.05 kilohertz. Let me fix the units there. And that's all we have. Any frequencies that we introduce at or above 22.05 kilohertz would be artifacts. Could be harmonics, could be, who knows, replicas of, because we know that this is really just a sampling operation, this upsampling. And what we actually are going to get in the frequency domain is replicas of this baseband, of this low-pass signal, replicated at high frequencies, like we would in sampling. Go ahead.
No,
You're good. Okay. So we want to get rid of those replicas at high frequencies, and we do this by using the right low pass, or a good, not the right, a good low pass filter. There are many possible FIR filters. It could even be IIR if you wanted to. It doesn't have to be FIR. For communication systems, we're going to use FIR filters. For image processing, we'd use FIR, but for other applications, it doesn't have to be FIR. Audio doesn't have to be FIR, for example. All right, so let's look at this filter that we want. All right, so the filter really is going to enforce the sampling theorem for the signal that we started with. The sampling theorem says, right, that so this is the byproduct of the sampling theorem, that F max is less than half the sampling rate. And this sampling rate is at 44.1 kilohertz. So it means that through the upsampling operation, I'm going to be introducing these frequencies between 22.05 kilohertz and half of 176.4. So between 22.05 kilohertz and 88.2 kilohertz, I have artificial frequency content that was not there in the original signal prior to upsampling. So let's get rid of those as best we can, those artifacts that we introduced at least at high frequencies. Now, so what filter specification do we need? Well, again, I mentioned it's a low-pass filter, and the next thing is to figure out what frequency 22.05 maps to in the domain, the frequency domain used by the FIR filter. And we know this relationship from all the way back to, I'm feeling homework 0, but I know homework 1. It's been a long time. So what's the relationship? To go from a continuous time frequency to a discrete time. 2 pi f naught fs, and I got to get the right fs, so I'm going to go fs, it's this fs. All right, so it's the fs we actually operate at. I'll call it fs prime. Okay. And if we do the numbers on this one, it's going to be 2 pi, f naught is going to be 22.05 kilohertz, and then fs is going to be L times that. It's L times the original sampling rate, which is 176.4 kilohertz. Okay, so you work the math on this one, and we get pi over 4. But more generally, we're going to get pi over L, where L is the upsampling rate. And for the following reasons, because the F max that we have is 1/2 the original sampling rate, or less than, you could say less than, but we're just less than or equal to is fine here. So we're going to do, because we really want to get rid of 22.05 kilohertz and higher. Okay, so we're going to put this pi over 4 in the stop as our stop band frequency. So the sampling rate across the upsampler increases by a factor of L, the upsampling factor. And the max frequency doesn't change. It's still half the original sampling rate. So what I end up with then is this ratio is really, I want to put this. So this sampling rate, the stop band, is going to be 2 pi times L times the original sampling rate. And in the numerator, it's half the original sampling rate. Right, so we end up with pi over L. Just from enforcing the sampling theorem applied to the original signal that we started with prior to upsampling. All right, that at least gives us the stop band frequency of the FIR filter. How do I get the passband frequency from that? I know the stop band frequency. How do I get the passband frequency? Do something similar? Do the same thing? It's the other way around. So it's 1.1 times the stop band frequency is 1.1 times the passband frequency. In other words, we generally allow a 10% roll-off from passband to stop band. So the passband frequency would be 0.9 times the stop band. Just as a general rule of thumb for filter design. So that would give a 10% roll-off, right, from passband to stop band. And then for the passband and stop band ripple, this would be tied, to the number of bits that we want to support per sample, the quantization level we have, and we'll talk more about that when we do quantization lecture in lecture 8. But it's related to the number of bits. Go ahead. You can do either one. So here we know what the stop band is. We've got to find the pass band. In other cases, we know the pass band frequency, and we don't know the stop band. But no matter which one we know, it's a 10% transition band from pass band. You know, it's a rule of thumb. It's just from designing filters, which you did on homework and so forth. Okay, so it gives us an FIR filter that we want, and then, you know, based on the application, we can, you know, then do more issues about what's the stop band frequency, what's the stop band attenuation, what's the pass band ripple, those kind of things, based on the application. If it's just raw support of 16 bits, then we know what's the stop band attenuation going to be for this one, for 16 bits of quantization accuracy. Remember the 13.5 dB. It would be the averaging filter, but we can have FIR filters doing better than 13.5 dB. But 13.5 dB would give me basically 2 bits of quantization support. How many dB of stop band attenuation do I need for 16 bits? 6 dB per bit for one channel quantization. So it'd be 16 times 6, somewhere around 96 dB. That's incredible stop band attenuation. Pretty incredible. Okay, but, you know, long enough FIR filter, we could probably do it, but. Okay, so all right, so I've given you the story in the time domain and the frequency domain, and so after the FIR filter is applied, we'd like to be able to connect the dots that we started with, the samples that we started with prior to upsampling, and the FIR filter essentially will filter the samples we know, which are shown right, which are shown here. Those are the samples we know. You have the zeros inserted between them, or after each one, however you want to look at it. And where our FIR filter now will try to connect the dots that we know, show here in green, to get a smooth output. Right, so now we've filtered out, we've made this signal smoother. There's less jumps that you can see here from index 0 to 1, and then from 3 to index 4. It's a sudden jump here. Right, so we've smoothed over those sudden jumps. We've essentially connected the samples that we know by connecting the dots, and the pulse shape that let's say the impulse response to the FIR filter tells us how we connect those dots. So we could use a sync impulse response truncated. We could use race cosine. We could design the FIR filter using Parks-McClellan, Kaiser. You know, pick your favorite method. Okay, there's a question. Yes, the question of the commonly 70 or 80 dB. The answer is yes, your board is this way. The data converter on your board, we'll talk about that later on. But for higher end audio, they're going to go to 100, 110 dB.
So there are certain, like,
Yeah, 16 bits is not that much, is not a problem anymore. So having a data converter giving you 16 bits per sample at an audio rate of 44.1 or 48 kilohertz or 96 is really not that difficult today. It's the 20 and 24. 24 bits pushes what's achievable in A to D conversion. That's correct. That's correct. There's a lot going on, and also the way that audio data converters are implemented are not the cascade of filter, sample, quantize. It's more complicated, and we'll get to that. Okay, any more questions on this? This is very important stuff. This is lab 5, 6, and more. It's all the homework sets from here on to the end. So this is an audio application, but the same idea is going to be used in the baseband transmitter, or the baseband subsystem for the transmitter. Let me go back one slide. So this was the context for the communication system, in that we start with symbol amplitudes that are from a constellation map. It would be plus or minus 1 if it's 2PAM, plus or minus D. Symbol amplitudes, those are streaming at a symbol rate. I use upsampling by L. So now in the communication systems context, L is the number of samples per symbol period. So L is also the upsampling factor, but in this application context, it's also the number of samples per symbol period. It's the oversampling that we're doing versus the symbol rate. So we increase the symbol rate by a factor of L. We then FIR filter. So this filter here is an interpolation filter, but in the context of communication, it's a pulse shaping filter. And then the D to A converter is going to be driven at the sampling rate. The sampling rate is a product of the symbol rate and the upsampling factor, or samples per symbol. So the sampling rate is L times the symbol rate. Okay, so those two clocks are related to each other, which is good news for the receiver. And there are some communication systems that it's not this simple, I will tell you, but for a single carrier, for the kind of communication systems we'll do, it is this relationship. So if I lock onto one clock, I can help lock onto the other, as long as I know what L is. Okay, now this is the part of the baseband processing. Then after the D-to-A converter, it will go through some subsequent processing before final transmission. So a modem consists of a baseband subsystem and some analog front end. So this class is focused primarily on the baseband transceiver. We don't do very much on analog integrated circuit design. That's another set of classes for the analog front end of the modem. Okay. So if you interview, tell them that you learned about transceiver design, and you're good. If you tell them you learned about modem design, then it's implying that you know the analog front end really well, and you've designed one, which you may have done in another class, but not this one. All right. So for this class, it would be baseband, or just call it transceiver design would be fine. You could say baseband transceiver, I suppose, as well. Now, we certainly talk about impairments of the analog front end and its impact in the transceiver design. So let's move on to 13.9. Now, if you look at this standard way to do interpolation in discrete time, it turns out to waste an awful lot of multiplication and addition operations. So let me give you an example with 4 samples per symbol period. So when I use the word symbol, it could mean symbol period, it could be symbol amplitude, it could be symbol of bits. So 3 different ways, I suppose, it could mean something. In this case, it's a symbol period. Our pulse shape, we're going to use a relatively short pulse shape for this example, just so I can enumerate all the possible combinations. The pulse shape here will last for 2 symbol periods. So this means that from earlier slides, this is NG is 2, which is the number of symbol periods over which the pulse shape lasts. And then in terms of samples, well, it should be 2 times L. So we know that if we have 2 symbols and we have L samples per symbol period, then we have 8 samples total in the impulse response for this FIR filter that's doing the pulse shaping. Okay, let's look at where the inefficiency comes in. So if I do the standard, I have a bunch of bits, and I encode them using a constellation map, pulse amplitude modulation. I get out a bunch of symbol amplitudes, plus D, minus D, plus 3D, minus 3D, whatever the map gives us. And the upsampler is going to append zeros after every symbol amplitude. And if we look at what happens, so here's 1 symbol period. So I have the symbol amplitude A0, and I've got this in streaming form, so A0 is the most recent value. I append 3 zeros after that, and if I look at this, I go, I got artifacts, I want to do an FIR filter on this. So that's great, but now if I look at the calculations involved, the FIR filter is going to do a lot of math with 3 zeros. We're going to multiply the FIR coefficients against these 3 zeros. I'm wasting my time. Why am I multiplying by 0? So there's a more efficient approach, which is a pulse shaping filter bank, and it gets rid of these multiplied by zeros. It's just incredibly efficient. It's a win-win. You don't lose any precision in the calculations, and you remove all the unnecessary multiplication by 0. It's a rare case where the design trade-off is so much in your favor that you just do it. It's incredibly in your favor. You reduce memory usage, you reduce memory I/O, and you remove multiply by 0. And you don't lose any signal quality. Doesn't happen much. Go ahead. All right. So let's go through it. So the output of the FIR filter for my pulse shaping is the convolution of this input signal, which is the upsampled signal, and the impulse response of the FIR filter G of M. So if I look at this convolution, I'll do a flip and slide of my X of M, which is now 3/4 of the time 0. So I'm going to flip and slide X of M about G. So G is my FIR filter. It's a tap delay line. I do my flip and slide. As I flip and slide, every time I slide 1 point over, I end up multiplying. So what's the first value? So S naught, as I show here, if you flip and slide, it's going to be A naught, G naught. Okay, so that's fine. Not wasting any work here. You look at S1, again from the convolution approach, and now what I have A naught times what? G1 plus A1 G0. Oh, guess what? So G0 is A naught, but G1 is 0. What's not G1? Sorry, A1. Sorry, A naught is a non-zero value. It's going to be plus D minus D, whatever. But A1 is 0. So if I do the direct form FIR implementation, I'm multiplying by 0 an awful lot of the time. Oh, this is an A1. I'm sorry. This is not A1. That's what the confusion is. All right, this is X. So this is convolution of X and G. So I have X 0. Now I have X 0, X 1. Sorry about that. And this is, that has value of 0. So I'm wasting the computation. Because I know the structure of the input signal into my FIR filter, and I can take advantage of that. Okay. So then what happens is that, so now what is that? Well, X of 0, we know what X of 0 is. That's A naught. So that goes to A naught. And X of 1 is 0. Okay, so I look at the calculation. So S naught is simply A naught G of 0. That's good. S1, I only have one multiply to do, because the other multiply, I'm just multiplying by 0, so why do it? I then keep the flip and slide going, and again, I just have this one non-zero value of A naught going through the delay line. And then finally, S3, I'm still just doing one multiply operation. Okay, now, once I get to S4, now A1 has entered. Now the next symbol has entered the story. So the next symbol of samples have entered this. So A1 has now entered the input to the FIR filter. And now I have, instead of 5 multiplies and 4 adds, I just have 2 multiplies. I just have to worry about A naught, A1. And so forth. I keep going. So there's a nice pattern that's emerging. And you'll notice that the offset between the samples that I need out of the coefficients I need out of G are offset by 4. And the starting point changes by 1 as I go down from top to bottom here. So I go down from top to bottom. I start with G naught, Remember, G naught is the impulse response of the FIR filter, my pulse shape, and I need G4. The next output sample, I need G1 and G5, which is 4 coefficients later. Next one down, G2, offset by 4, G3, offset by 4. So now if I want to design a signal processing structure to do this efficiently, I can do it through a filter bank. Now normally you would think, yeah, gee, it's a filter bank, it should take more operations. And yes, that's often the case. But for this case, it's going to take fewer operations because we've tailored the filter bank structure to remove the multiply by zeros. We just don't do them. So it becomes actually more efficient. Go ahead.
You're saying like these filters are capable of like this, like right there indexing that they will just pick up the point that I want to multiply by. Right.
Well, if you just this is the question is the filter like smart enough to figure out what to pull off? This is just what really happens. These equations are what really happens if I remove the multiply by zero terms. I mean, really what I have, let's say for example in S1 I have these 2 terms, in S2 I have 3 terms, right? I have x naught times G2, x1 times G1, and x0 times, x0 times, yeah, G2. Let me sort this through on the, give me a second. So I need x1, x naught, G2, so let's run it out. Right, x2 is my most recent sample, and it gets multiplied by G naught, right? Now remember, 2 of these terms go to 0, right? So there's no reason to calculate them. So the one that we care about, so which one do we care about? Yeah, just the first one, right? And then the rest of these just go to 0. Right, so that goes to 0, and that goes to 0. So why bother calculating them? Right? I mean, how to go from the direct, this upper half block diagram to the lower half? I haven't, hang it, we'll do that now. That's the next step. So now if I look at what I need, so what I have streaming into all 4 polyphase filters are the symbol amplitudes, A0, A1, and so forth. I don't need those zeros. Why bother?
How do you do that?
Oh, it's just I take the value right off the encoding step, right? So right off the encoding step, I just take the stream of symbol amplitudes. And in parallel, I send it through 4 short filters instead of 1 long filter. And each short filter, I have 4 of them. Well, in this case, I have L of them. L is 4. So I have 4 of these short filters called polyphase. And the reason they're called polyphase is they correspond to a different delay. And delay in time is change in phase and phase shift in frequency. So what do I need? So to compute S4, what do I need? I need to have I just need 2 coefficients. I need G naught, G of 0 and G of 4. I don't need any other of the impulse response coefficients. So that's my first filter. It's just 2 taps, and it's G naught and G4. Very short filter. And that will give me S4. Now it also gives me S0, because you look at S0, all I need for S0 is G naught out of the impulse response. So this will if we keep doing the calculations, this first upper polyphase filter gives me S0, S4, S8, and so forth, which is nice. The next polyphase filter is going to give me S1, S5, S9, etc. And I look at what's in S5, I need G of 1 and G of 5. And that's it. I don't need anything else from the impulse response. And then I keep going. So for S2, S6, I need G2, G6. And then for the last branch or part of this, I need G3, G7. and I'm finished. A nice, fine-looking polyphase filter bank. Now this is wonderful. I'm now computing S naught with only 2 multiply operations and 1 addition. I'm not doing it with 8 multiplies and 7 additions, which is good, because if I did it the direct form way in the upper block diagram, I'll be multiplying by 0 3/4 of the time, wasting cycles, wasting power, whatever. Okay, so if I look at now, what do I have to do? Well, I now have to pull off the values that I need in the right order. So I need to pull off, so I really want to compute the same output that I had in the upper block diagram, S of m. And to do that, I'm going to pull out S naught, and then I'll pull out S1, and S2, and then S3, and then go back to get S4. I'm going to cycle through the outputs. Okay? And this is called a commutator. It's a periodic structure. We start with the upper branch, and then work our way to the next branch, next branch, next branch, and then start back to the beginning. And just do this over and over again. Because the commutator comes from rotating machinery. We borrow the term. Now, if you look at the operations here, again, not only have I removed all the multiplied by zeros, let's see, what else have I done? So if I don't have the zeros, I don't have to store them in the FIR filter, in the polyphase filter bank. Right? I don't even have the zeros here. So I don't have to store them. So I reduce the storage by a factor of L of current input and previous input values. There are no zeros anywhere. I have to store them. Number of coefficients doesn't change. They're just permuted. So if I look at all the coefficients, of all the polyphase filters, I still have 8. They're just permuted. So I start with G naught, and I take every Lth coefficient. So I start with G naught, go G4 because L is 4, G naught, G4, and I'm finished. Next filter, G1, G5, I'm finished. G2, G6, I'm finished. G3, G7, I'm finished. So these polyphase filter these polyphase filter coefficients are just permuted versions of the original FIR filter for pulse shaping. You'll implement this in lab. So let's compare the two ways of doing this. So we have the direct form in the upper block diagram, sort of the standard way of doing interpolation. And then, again, this is not just communication systems. Anytime we do discrete time interpolation, where we have an upsampling block followed by an FIR filter, we can do this polyphase filter bank. Go ahead.
So in the bottom half, I'm confused. Is there not any upsampling?
Where is the upsampling happening?
I guess.
And where else? So I'm upsampling the filter by permuting the coefficients of the original pulse shaping filter, this GT-sim here. So I'm permuting, I'm not upsampling, but I'm permuting the coefficients. But where's the upsampling on the data being performed? It's in the commutator, right? So if you look at the commutator structure, I'm cycling through these outputs.
Oh, okay.
That's where it's happening. So you can think of it as I'm really swapping the order, be careful how I say this, but you're essentially swapping the order of, instead of doing upsampling and filtering, you're really doing filtering and then commutation. So you're really doing the filtering and upsampling after that. I gotta be careful because the commutator is not an upsampler, but it helps us complete the effect of the upsampling. Another way to think about it, we're doing the filtering at the lower rate. In this context, that lower rate, the lower sampling rate, is the symbol rate. So the filtering is happening at the symbol rate, not the sampling rate. So I have the same number of FIR coefficients, but I'm running those coefficients as a filter at the symbol rate, which is L times slower than the sampling rate. So I get a factor of L savings and multiplies per second. It's one of these win-win-wins. I mean, you win every way you can think of, and you don't lose any signal quality at all. It's a rare event. Okay, so these are equivalent operations. Whether we upsample by L, then FIR filter for pulse shaping, or we do polyphase filter bank followed by a commutator. The same answer. All right, so I'm going to go on to an example. All right, so that's another example. So in this example, from a very much a communications point of view, we're going to have our original pulse shape is 24 samples in a duration. And you'll see the pulse shape. What kind of pulse shape is this one? Sync, truncated sync. So you could also say raised cosine, you'd be fine because raised cosine is just a generalization. So when alpha is 0, we have the sync for the raised cosine. When the roll-off factor is 0, the raised cosine becomes the sync. I have 4 samples per symbol period. So if I kind of talk about this in earlier parameters, so the 4 samples per symbol period, that means that L is 4. And how many symbol periods are in one pulse shape? How many symbol periods are in one pulse shape? Six, right? So I have 24 samples per pulse. I have 4 samples per symbol, and the units just work out nicely, right? We get symbol periods per pulse. Just as bad as I started with. Okay. So how many coefficients will each polyphase filter have? Okay, so the original FIR filter has, right, the original pulse shaping filter has 24 samples, right? So that's the length of the impulse response of the original pulse shaping filter. But for the pulse shaping filters, how many coefficients per, first of all, how many polyphase filters do I have? I have 6. I have 3. We'll get there. 4, there you go. All right, good. So there are 4 filters, and each filter now has how many coefficients? 6. Because we have to find a home for each of these 24 coefficients of our original pulse shaping impulse response. All right, so here's our pulse shaping. Here's our original pulse shape. It's a sync. And so to get, and it's plotted in MATLAB, so I'm starting it's just a stem plot, or not stem plot, it's just it's a plot with the samples connected, right? So it's just a regular, plot command here. But I didn't start at 0 where I should have. So you just have to forgive me there. The MATLAB default started at 1, should have been 0. So forgive that. All right, so here's really the first, so what do I need for the first polyphase filter? I need the first coefficient, and then what after that? If I do every 6, then I want to get 4 coefficients. So it has to be every 4th. Every 4th. Okay. All right. So I start with G of 0. Again, I really meant this to be G of 0. And then I want, 1, 2, 3, 4. Now, in the printed version, I have X's where I'm going to take the values. And they may be hard to, back row, is it hard to see? The X's? No, you're okay, good, all right. So this is G of 4. 1, 2, 3, 4, G of 8. Do you see a pattern? They're all zeros. Okay, now this comes back to the earlier question of if we upsample and then apply an FIR interpolation filter, how do we know that the original samples are not changed? The original values before upsampling were not changed. is there a special pulse shape, or there is a special condition on the impulse response of the FIR filter? The answer is yes. And if you look at this, essentially what happens is the values at the start of the symbol periods in the future and the past have to be 0. That is to say that we don't include contributions from those particular values. And if we do that, we don't in any way affect the original sample values prior to upsampling. They are carried through the whole interpolation process. If I don't get the 0 crossings here, then I do change those values. Not the end of the world, but depends on application. All right, so here's G of 12. G of 16 and G of 20. Now and again, this really should be 0. It's intended to be index 0. I'm just off by 1, so yeah, sorry about that. So I'm going to take G0 and then every fourth coefficient. Go ahead.
You said that they all have to be 0. Is it okay for
Oh, I'm sorry. The other, so the G12. This is the current. This refers to. If this is the causal. So if it's not the causal pulse shape, this actually is the current symbol period. But to make it implementation, we shift everything to make it causal. So this now becomes the current symbol period, which means we have to buffer we have to pull this off by buffering. So I have to, right.
Like whenever you had the very beginning, you had the zeros on each of the peaks, like at 0 and 4. That's essentially that.
Right. So this would be, you know, the FIR filter fully loaded, fully responding to the input, right? Normally the initial values are 0. These are coefficients, but separately we have the initial values in the tablet line. They're zeroed out for LTI properties, for necessary conditions for LTI properties. So I have, so I'm going to buffer, 3 symbols before I do any transmission. Another way to think about it is that whatever comes off of the FIR filter or the polyphase filter bank version, I'm going to throw out at least the first 2 symbols. Because the filter hasn't fully responded yet. This pulse shaping filter hasn't fully responded. You throw out the group delay, in other words. So you throw out the first 3 if you wanted to. Okay. Actually, you don't want to you want to throw out the first 3, which is the group delay. Half the samples, basically. All right, so that's the first polyphase filter. And you'll notice, so for this particular pulse shape, 5 of those values are 0 and 1 is not. We'll go pretty quickly over the next 3. So here's the next polyphase filter. And you'll notice that we'll pick this value and then every fourth value. And now it's no longer all zeros. So those are the coefficients for the next polyphase filter. This is the second channel, or polyphase filter number 1, if the first channel is polyphase filter number 0. Next polyphase filter, start with offset of 2 from the beginning, and then take every fourth value. And then the last polyphase filter, I start with an offset of 3 from the beginning, and then take every fourth. So all the coefficients are found at home, all the original coefficients in the pulse shape have found a home in the polyphase filter structure. Okay, so we'll leave it there for next time. Do the design trade-offs for next time. Again, please pick up homework if you haven't done so. Thank you.